Good morning, chemists. How are you? Are you guys feeling like spring break should be nearby, but there is no spring break? That's how I'm feeling. For sure, but it's okay. We'll make it. We're close to having like shorter weeks, which will be nice. But we're not to a full week off. But anyway, remember that your paper's due soon. As you turn it in, submit it as a PDF. Everybody hearing me? Submit it as a PDF, because if you submit something as a Word document, then it's possible that it will change the formatting. So whenever you submit anything, submit it as a PDF. And then another thing, make sure you're showing up to office hours prepared. Make sure you are prepared for office hours, not when you get there for our 20 minutes, that's when you start looking up questions. Look up questions before you show up so that we can make the most of our time together. Some groups are showing up with lots of questions prepared, and so we are hitting a whole bunch of points as we go through. Some groups are showing up with nothing, and you're basically wasting that whole week of office hour time. So if you're showing up with questions from homework, problem sets, exams, different concepts from lecture, that's a good thing. You want to show up with questions to help yourself to do well on the exams. If you don't ask questions now, the questions will come up, and that's not good, right? You want to make sure you're doing well in this class. And the way to do that is to keep working on all this stuff every day, and also to ask a lot of questions. All right, so we're in our nomenclature talking about benzene and these aromatic compounds. We call them, since they're aromatic compounds and alkenes, we call them arenes. So aromatic and arenes, those are interchangeable. So if it is a substituent, then we would put AR, saying that it's an aryl group. So any kind of a benzene ring with something attached to it, we would call it an aryl group. That's just a general term for an arene that is a substituent on something else. We would call it aryl. If that substituent is specifically benzene, though, then that's called phenyl. So phenyl and phenol are two different things. So remember phenol, OH, but phenyl is this, where we have a benzene ring that is just a substituent, right? When I do that squiggle line, that just means this is connected to something else. So as a substituent, this is called phenyl, right? Any substituent ends with YL. So as a substituent, we have a phenyl substituent, and then we also have a benzyl substituent. So when we have a phenyl, so a benzene ring with another carbon, that's called a benzyl substituent. So phenyl is just benzene ring, but if we add a carbon coming off of that, then that's called a benzyl group, or phenylmethyl. So here we have a cycloheptane with a phenyl substituent, so phenyl in the name. And here we have what's called phenylmethanol. The common name, though, would be benzyl alcohol. So let me redraw it like this so that you can see it's a carbon, but then with an OH on it. And so hopefully you can see that this whole thing is called benzyl. So benzyl alcohol, whereas this whole thing is called phenyl. There's no additional carbon attached to the benzene ring. So let's talk about this a little bit further. So when we have a benzene ring attached to this ring, so here the ring is 7 carbons, that allows for our benzene ring to be a substituent. So we have a 7 carbon ring, and so now the benzene ring isn't the main thing. But it doesn't matter if we have a carbon chain. That carbon chain can be 7 carbons long. With that 7 carbon chain, this is still called benzene. This is just called heptyl benzene, all one word, right? Heptyl, 7 carbon substituent on a benzene. But because this is a 7 carbon ring, Now the whole thing is a cycloheptane, and the phenyl is a substituent. If we have a ring that is larger than a six-membered ring, so a ring larger than a six-membered ring, that's when we have our a benzene ring as a phenyl substituent. So let me go back to this example also. So remember we had this compound. And so we said we were going to name this as phenylmethanol. Why is this going to be named as phenylmethanol? Because the highest priority group is this one carbon with the OH on it. That's our highest priority group. Here we had to have a 7 or more carbon ring attached in order to have the benzene as a phenyl. But if there is some kind of a carbon chain with an OH on it, now this is high priority. And so our benzene ring becomes a substituent. And so this is called phenylmethanol. That's the IUPAC name because there's an OH there. So let's look at this heptylbenzene. So we call this heptylbenzene. So if we have this 7 carbon chain, but now there's an OH here, how do we name this now? Well, now this is no longer a benzene. We number the carbon chain getting to the OH as quickly as possible. So the OH is on carbon 2. We still have a 7 carbon chain, but now this is a substituent. So now we have a substituent on carbon 1, this phenyl substituent. And so the name for this is 1-phenyl 2-heptanol. As soon as you add in an OH to the chain, now it becomes a long chain or even a short chain. Here we only had 1 carbon at the bottom, but that becomes our main chain, and the benzene ring becomes a substituent. But as long as there's nothing high priority on the chain, you can have a chain as long as you want. That's just going to be a substituent on your benzene ring. But if it's a ring that is more than 6 carbons, then we have to name it as the ring, the cycloalkane ring, with a phenyl as a substituent. So remember also, if I, instead of having this compound, if I have this compound instead, and let's say I put the OH here, instead of being attached to that carbon, now this is a phenol. And phenol, that has to be carbon 1. This is carbon 2. So this would be 2-methyl phenol. Phenol, phenyl. Phenol, phenyl. YL is phenyl. Phenol is OL. Questions on this?
Just like in general, not even like talking about like having benzene rings in the compound, does the OH always take priority over like chain number? Like OH always has to be in the main chain regardless of like if there's a longer chain present?
Correct. But when we start adding in aldehydes, ketones, carboxylic acids, those are higher priority groups. So those will have to be part of the main chain. But right now, we haven't talked about anything higher priority than alcohol. All right. So now we're into 15-2, talking about properties of our benzene ring. So remember, for benzene, we have our 600 ring. And for the 600 ring, every one of those carbons has a single bond to it and a double bond to it. So that means every single carbon is sp2 hybridized with a p orbital, right? What did we say for sp2? What does that look like for the electron configuration? sp2. And so there's still a 2p orbital. So this is what it would look like. We're talking about this 2p orbital. That's the 2p orbital that we're looking at above and below. And so with the 2p orbital, we know that each of the carbons has an sp2, so we can see the hybridized orbital. Here's another hybridized orbital, and then here's the third hybridized orbital, right? We have 3 of these sp2 orbitals that can make those sigma bonds, but then to make pi bonds, we need unhybridized p orbitals. So with this now, we have 6 pi electrons. The pi electrons are here, right? We have 1 pi electron here for 1 carbon atom, but we have 6 carbon atoms, which means we have 6 pi electrons. These 6 pi electrons we know are delocalized because we have the other resonance form that is possible. So we delocalize all those electrons around the ring. And so we end up with this electron cloud above and below the ring. Why is it above and below? Because that's how the orbital looks like. That's how that 2p orbital looks for each of the carbon atoms. It has an area above and below the plane where the electron density can be. And so we get this circular pi cloud, and we can see here our electron density is delocalized. All 6 of those carbons are sharing the electron density equally of those pi electrons. So with this, let's think about the stability of benzene. We know it has these 2 resonance forms. We know we have these 6 electrons that are delocalized. So how stable is this? So we were looking at heats of hydrogenation, and we said the higher the heat of hydrogenation, the less stable the starting material is, right? More heat release, less stable starting material. So if we have 1 double bond in a ring, we would release 28.6. But if we have 2 double bonds where they are conjugated, we would expect it to be additive. We would expect it to be 2 times negative 28.6 kilocalorie per mole, which we would expect to be negative 57.2. Just for 2 alkenes. But because it is conjugated, the value is lower than expected, which means that this conjugated is more stable than just 2 alkenes separate from each other. If the alkenes are in conjugation, it's more stable than the alkenes being non-conjugated. So we have this resonance stabilization that makes the conjugated diene more stable, right? A lower value than what we would expect for a non-conjugated, but still a diene. 2 alkenes, but they're not conjugated with each other. We would expect it to be 57.2. So it's lower than expected. So it's lower by 2.3 kilocalories per mole. This is because of the resonance stabilization. The resonance stabilization is going to allow for this value to be 2.3 kilocalories per mole, lower than expected. So then what would happen with benzene, right? If we're adding in another double bond, then we're talking about having more of these alkenes in conjugation. So here we would have these 3 alkenes, and so we would expect it to be 3 times 28.6. We have 3 double bonds. So 3 times 28.6, that's what we were doing before. Every time we have another double bond, we would expect it to be, another 28.6. But then we also can say that, okay, remember we said 2.3 is how much lower it would be because we have that diene in conjugation? Well, here we have 3 diene groups. What are those 3 diene groups? If I call this 1, call this 2, and I call this 3, my 3 diene groups would be 1 and 2, 2 and 3, and then 1 and 3. Those are my 3 diene groups, 3 conjugated diene groups. I guess I should write conjugated. So I have my 3 conjugated diene groups, 1 and 2 as a diene, 2 and 3 as a diene, 1 and 3 as a diene. So we would expect, okay, we multiply 3 times 28.6, and then we add in the resonance stabilization for having those 3 groups of dienes. We would expect the value to be negative 79.9. If what we were just doing is correct, then when we hydrogenate, we would expect about 79 kilocalories per mole of energy to be released. And so what we would say is, okay, if we have cyclohexene, 28.6 released. If we have this conjugated diene, we said 54.9. So we said, if we apply that, then if we have this 135 cycloheptatrienyl type compound, where we have our 3 different pairings for the conjugated dienes, we would expect it to be 78.9. But this is what we actually have. For benzene, actually only 49.3 kilocalories per mole of energy is released. This is what is in reality. We would estimate this, but this is what we measure, which means that benzene is more stable than just having these 3 dienes that are in conjugation. So we get this lowering in energy from what we would expect. And look at this, it's even lower in energy than just a regular conjugated diene, cyclohexadiene. Benzene is even more stable than that. We see that it is way lower than expected, about 30 kilocalories per mole lower in energy than expected. What is this due to? This resonance energy, this stabilization is because benzene has this delocalization of these pi electrons. Because we have these 6 pi electrons that can move around and around and around and around the ring, it's not these 3 separate dienes. Everything is delocalized among all of the atoms of the ring, which stabilizes this system. And so we would call this resonance energy, like you see here. We could call it delocalization energy. But what we really call it is aromatic stabilization or aromaticity. Aromaticity is the term for this stabilization. Now, remember we talked about our benzene rings and benzene-containing compounds. We said they have a smell. They are aromatic. Now we're talking about aromaticity as a thermodynamic term. Thermodynamic meaning this stabilization, this lowering in energy based on the fact that we have these 6 carbons that are sharing these 6 pi electrons equally, and they're moving around and around in a ring. This stabilizes benzene. So benzene's aromaticity is very, very important. Benzene's aromaticity prevents it from participating in regular reactions. So we'll talk a lot about aromaticity, losing aromaticity, gaining back aromaticity, where we're really talking about having these 6 electrons that are delocalized around the ring. Questions on that?
I have a question. Is there a way to find the delta H of the benzene ring like we did for the 3 conjugated diene ring?
Well, you can't. So we try to calculate it, but the calculation doesn't work here. If with what the measured value is, you can see that there's actually a lot more lowering in energy based on aromaticity, and so this would be the value that you'd have to use. We were using a smaller value, that 2.3, but now it's about 30, which is the stabilization factor there for a benzene ring. So yeah, you can calculate it now that I've told you that, but you won't have to calculate that kind of thing. All right. Other questions? All right, so looking at benzene, where we have our 3 double bonds in the ring, versus having this hexatriene. Where we have these double bonds here. Whoops, hold on. Oh, yeah. This isn't going to work. Hold on. There we go. So we have our 3 double bonds. So it's still conjugated, right? Double, single, double, but it's in a straight chain versus our 3 double bonds, double, single, double, where it is in a ring. So we're looking at still 6 atomic orbitals, right? For both of these, we have 6 atoms. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we have 6 atoms. And so we have 6 atomic orbitals, and we mix those together to make molecular orbitals. And so we're going to make 6 molecular orbitals for each of these cases. And so for our 6 molecular orbitals, we have psi, 1, 2, 3, all the way to 6, and we have pi, 1 through 6. So for psi 1, 2, and 3, we can see that they're all lower in energy than our original atomic orbitals, and then 4 through 6, they're all higher in energy. Same thing with pi 1 through 3 and pi 4 through 6. But the difference here is that we are lowering the energy as we look at the energy for pi 3 versus psi 3. That's lower in energy. Same with pi 1 and psi 1. That's also lower in energy. So we have these 2 bonding molecular orbitals that are lower in energy than what they would be if it was a straight chain. Because we have this ring, we get these different molecular orbitals. And then if we look here, yeah, our pi 2 is a little bit higher in energy, lower in energy than our psi 2. This is a little bit, we have to go up in energy to go to psi 2. But overall, psi 1 and psi 3 are lower in energy, which has lowered the energy overall of our system. So if we look at this same thing, but just with lines, instead of the structures of the molecular orbitals, you just see the lines. So we have our psi 1, we see our psi 2, and psi 3. You can see the lowering in energy compared to pi 3, a little bit higher in energy compared to pi 2, and a little bit lower in energy compared to pi 1. So it's a cumulative lowering of these orbital energies for our bonding molecular orbitals. So that's why benzene is more stable. Overall energy is reduced, so stability is increased. Stability is increased as we go from being a straight chain to a ring. Questions on that?
Yeah, I actually have a question. Why is psi 2 higher in energy than pi 2 again?
It just ends up being a little bit higher in energy just because of where the nodes are. All right, let's talk about spectroscopy. So get out your spectroscopy sheet. Have that beside you. Let's start off with IR. So benzene has basically a whole class of everything on its own. It is different from everything else. And so we have a lot of different things to look at here. So turn your sheet over to where you're looking at the image that has these 2 things in it. So 3030 for IR, that's going to be the CH of a benzene ring. And then 1500 to 2000, you'll find the carbon-carbon double bond stretch. So just one of the stretches of the carbons of the benzene ring. So you'd have to have those 2 things to know you have a benzene. If you don't have this peak, that means you don't have a hydrogen on your benzene. And so every single carbon of your benzene has something else on it. Then we have these other peaks in the IR, and these I think are really important. They tell us a lot. So if you have a monosubstituted benzene, you would have to have both of these peaks. You'd have a peak between 690 and 710 and a peak between 730, 770. You'd have both. If you have a disubstituted that is ortho, you'll have just one peak here, 735 to 770. But it's meta. If it's meta, then you'd have, again, two peaks. If it is para, one peak in this region. So that tells you a lot. Just looking at IR, you know the kind of substitution on your benzene ring. If it's monosubstituted, ortho disubstituted, meta, or para disubstituted, then you'll also see these peaks. Now, look at where they are. They're in the fingerprint region, so you might not see them in real life, but I will definitely give you these peaks if we're doing an NMR IR problem. So let's look at this. We have metaxylene, 1,3-dimethylbenzene. So there's the peak at 3030, which tells us we have a benzene ring with at least one hydrogen on it. There's a peak at 2920, which tells us we have alkane CH. There's the peaks, both of them together, 765 and 690. You have two peaks in this region, so you need to look for the range that they can fall into. 765 and 690, really that could be either one of these. 765 could be in either of these, and 690, and also in here 765. So you'd have to look a little bit further than this, but what this is telling you is that you have a benzene ring, really that is meta disubstituted in this case. Both of those together tell you that. So I would give you numbers where it's not so, it's not as vague, potentially, where it can fall into both of those regions. I would give you numbers where it's only in one. All right, so that's our IR. Then we have NMR. So flip your sheet over, I think. Yeah, to look at the other side where the proton shifts are. So remember we had a allylic, right? And we said hydrogens right here would be anywhere between 1.6 and 1.9. So for this specific compound, this would be 1.68 parts per million. But that's an allylic carbon. We have the same thing. So remember we talked about this case where we had a carbon right beside the benzene ring? That's called benzylic. And so for that carbon, it's going to be more deshielded. The benzene ring is pulling away electron density. So this would be at 2.35 ppm for toluene. This would be toluene. So it's more deshielded being attached to a benzene ring, being the carbon attached to the benzene ring, the benzylic carbon.
Bless you.
Oh, thank you so much. And also for the alkene, remember we had our alkenes anywhere between 4.6 and 5.7. Now we have aromatic, which we know is benzene ring with a hydrogen on it. That hydrogen is what we're looking at. And so for that hydrogen, it would be anywhere between 6 and 9.5. So any of the hydrogens on here would be between 6 and 9.5 ppm. Unless there are electron donating groups, then it can be more shielded, electron withdrawing groups, deshielded, etc. So let's look at an example. Here we have a bromine on a benzene ring. The hydrogens closest to the bromine are going to be most deshielded because bromine is an electron withdrawing group. With those hydrogens, they're most deshielded, so they're furthest downfield, and also based on symmetry, they are the same as each other. These two hydrogens are also the same as each other, but because all these hydrogens are far away from the bromine, all of these end up showing up in the exact same spot where they're kind of overlaid. It should be one hydrogen and then two hydrogens, but you get three hydrogens where they're overlaid with each other. But we get our J values here that are on your sheet. So on the other side of your sheet, flip your paper over. You see we have now some J values for aromatic compounds. And so what we have here would be the blue being ortho-coupled to green. And so we get this large 6 to 9.5. And then blue is also meta-coupled to this green. And then this blue is also para-coupled to this green. So we have a bunch of different couplings that we can see here, coupling these hydrogens to one another. But it's kind of hard to see here. It's kind of messy to try to look at this. So let's look at something that's a bit cleaner. Here we have a para-disubstituted benzene ring. With this para-disubstituted benzene ring, we have an aldehyde, right? That's what CHO means. And so the aldehyde hydrogen, that's on your sheet. Aldehyde hydrogens are going to be anywhere between 9.5 and 9.9. We see this at about 9.75 for the aldehyde hydrogen. And then we have these three hydrogens, well, sorry, 6 hydrogens that are methyls, but they're attached to the nitrogen. And so these 6 hydrogens, they're pretty far downfield because they're attached to the nitrogen, but these 6 hydrogens show up together in a singlet because there's no hydrogen neighbors. All right, so let's look at what else we have here. We have our green and our pink hydrogen. So for these, the green are going to be further downfield because remember, this is an electron withdrawing group by resonance. But the pink are not as far downfield because nitrogen has a lone pair. Nitrogen is just like oxygen, where it can actually be an electron donating group by resonance also. It's just like oxygen. So for this, we have these 2 hydrogens that are green. They're showing up as a doublet because they have one hydrogen neighbor. We have these other 2 hydrogens that are green, also a doublet because they have one hydrogen neighbor. It's ortho. So ortho coupling, it's pretty large coupling, and so you can see the splitting there of that peak. So here, the J value would be 9 hertz for green and pink hydrogen. So pink has that 9 hertz coupling and green has that 9 hertz coupling. Para coupling is so small, we usually ignore it. So yes, green is also para to the pink, but we usually ignore the para coupling just because it is so small. You're usually not going to see that splitting. All right, let's look at another one. Here we have a methoxy, so we know that that's ether hydrogens. And so again, it's shifted downfield for those 3 hydrogens because they're connected to that oxygen. Here we have our TMS at 0. And then we have our nitro group, which is an electron withdrawing group. So we have our electron withdrawing nitro group. Anything close to that, so look at blue is in between 2 of these nitro groups. It's going to be very far downfield. Green is next to only one of them, one nitro group. It's ortho to one nitro group. So it is going to be downfield, but not as far downfield as blue. And then pink is beside this oxygen with 2 lone pairs, which we know the oxygen can be an electron donating group by resonance. So that's not going to be as far downfield. Now, looking at this, we have at about 8.45, we have our 1 hydrogen. This would be our blue hydrogen. Oh, whoops, sorry. Sorry, I did this in the wrong order. Let's start with 8.76. So 8.76 is our blue hydrogen, one hydrogen, right? And with that one hydrogen, it has one neighbor, and that neighbor is splitting it into a doublet. And so for blue, blue is meta to green. Blue is meta to green. And so we see this J value of 3 Hertz because this is a meta coupling. Then let's look at 7.23. Let's look at the other side. Let's look at pink now. It's still one hydrogen, and it's still a doublet, but now our J value from green to pink, or pink to green, is going to be 9 Hertz. Because pink is ortho to green. Blue and green are meta to one another, but pink and green are ortho. And then in the middle, we have our green, which is 8.45. 8.45, one hydrogen, but now it has pink that it can see and blue. So it's a doublet of doublets. And so it has both those J values. It has a 3 Hertz and a 9 Hertz coupling because it has something that is meta to it and something that is ortho to it. Para coupling is too small, so we don't see it, but we see our really nice doublet, doublet of doublets, and another doublet here. Really nice splitting. So finally, we can talk about our C13. Alkene or aromatic, they all show up in the same region. So everything for the alkene, we see that still for our aromatic rings. But look at our aromatic ring. If we have any symmetry, then the other side is also going to be 129.3. The other side is also going to be 128.5. So we're only going to see 4 peaks here because of symmetry. So you'll see fewer peaks with any symmetry that you have in your benzene ring. Same with this one. This is 123.4 and this is 129.5. We get that the symmetry, so fewer peaks than expected. Questions on the IR NMR? All right. Moving on to 15-5. So we can have our benzene ring, or we could fuse benzene rings together. So we have naphthalene. We've seen naphthalene before, right? We did a lab with naphthalene. This is the only one that you need to know on this slide, but know that there are others where we can fuse together 3 or 4. So tetracene, we have 4 together. Pentacene would be 5 benzene rings fused together. And then we can fuse them together with this angular fusion also, like we see with phenanthrene. So linear fusion, just putting a whole bunch of benzene rings in a line, but then we have angular fusion as well. But remember, all you have to know here is naphthalene. There is a specific numbering system for these, but we're not going to go over that, so you don't have to worry about that. But with naphthalene, remember naphthalene, with naphthalene, we have 3 resonance forms. With benzene, we only had 2. Naphthalene has 3. So more resonance forms, more stable. So naphthalene is technically more stable than benzene. It's aromatic, just the same as benzene. It has this aromaticity, the stabilization, where we are delocalizing now even more electrons around now 2 rings. So here we have 10 overlapping orbitals, and so we have 10 pi electrons that are delocalized. More resonance forms, more stable. So look at our fused aromatic compounds. Anthracene and phenanthrene, we have now 4 resonance forms, or we can do 5 resonance forms with phenanthrene. More resonance forms, more stable. So let's talk about how we know if something is stable or not. We have to use Hückel's rule. So Hückel's rule helps us to figure out, is something aromatic or antiaromatic? In order for it to be either aromatic or antiaromatic, it has to be a ring and it has to be conjugated. It has to be a ring and conjugated. So if it's planar, cyclic, and conjugated, and it has 4n plus 2 pi electrons, then it is aromatic. And it's stabilized by conjugation. But if it is planar, cyclic, and conjugated, but it has 4n pi electrons, then it's actually destabilized by conjugation, and we would call that anti-aromatic. So what is n? You know, n could be any whole number, 1, 2, 3, 4, 5, whatever. So 4 times 1 is 4 plus 2. That means 6 pi electrons. 4 times 2 is, if n equals 2, 4 times 2 is 8, plus 2 is 10. 10 pi electrons, that would be aromatic, and etc. But if it was just 4n, not plus 2, so just 4, 8, whatever, some multiple of 4, then that would be anti-aromatic. But it has to be planar, cyclic, and conjugated. If it's non-planar, or if it's not cyclic, or if it's not conjugated, that falls into this non-aromatic. So non-conjugated is also non-aromatic. And non-planar is non-aromatic. So let's look at this. Let's look at how we can apply Hückel's rule. So the first one we want to look at is cyclobutadiene. So if we look, we have 4 pi electrons here. And so what is 4 pi electrons? We know that would be 4n pi electrons, right? Where n equals 1. So we said 4n, anti-aromatic. 4n plus 2, aromatic. So we know that this is anti-aromatic. It is destabilized if we tried to overlap those pi bonds. Those pi overlap is destabilizing to the system. So we get this rectangular shape. Here we have a rectangle. So we go from one rectangle to the other rectangle as we go through a transition state. This is not resonance. This is not resonance. Energy is required. We have to add an energy to go from one resonance form to the other. So it is destabilizing to have this pi overlap here. So for cyclobutadiene, because it's anti-aromatic, we said benzene doesn't participate in reactions, but anti-aromatic cyclobutadiene can participate in regular alkene reactions. It is very reactive. So we can use it in the Diels-Alder. So here we have 2 different Diels-Alder reactions. So here is our cyclobutadiene in the Diels-Alder, where it is the diene. And here it's in a reaction where it is the dienophile, right? Either way, we can do this reaction. So we can use both of those. We can use it as a conjugated diene for our Diels-Alder reaction, or we can use it as just one alkene as the dienophile. The other alkene just stays the same. It doesn't react. So we can use it because it's very reactive. Let's look at another example. Here we have cyclooctatetraene. Cyclooctatetraene. And so with cyclooctatetraene, this is going to be where we have 8 pi electrons, right? We can see we have 4 double bonds. So we have 8 pi electrons. And so we know that that's going to be 4n, where n equals 2. This we would expect to be anti-aromatic, but it's actually non-aromatic. Why is it non-aromatic? Because it is non-planar. Non-planar, so non-aromatic. We can't get this to be planar. It doesn't want to be planar. And I would have to tell you if a compound is planar or non-planar. So I would tell you in some way that a compound is planar or non-planar. Assume that it's planar unless I say that it's non-planar. But here it's non-planar where we end up with these perpendicular double bonds. And so the double bonds have to be all in one plane for us to delocalize the electron density. We can't delocalize the electron density. This is very reactive. Each of these alkenes will react separately. Each of these alkenes will react separate to one another. They don't react as one compound. So this is non-aromatic. Then we have aromatic compounds. So aromatic, it has to be 4n plus 2 pi electrons. So here we have a compound called 18-aniline. So 18-aniline, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 double bonds, which means we have 18 pi electrons. 18 pi electrons, hopefully you can see that. N would equal 4, so 4 times 4 is 16, plus 2 equals 18. So this would be 4n plus 2. It's also planar, and so this compound is aromatic. We are delocalizing all that electron density. Look at all that red delocalized over all of these atoms. So I called it 18-aniline. How do we name it that way? Well, to name these compounds, we look at the ring size. The number of carbons in the rings tells us the number. And so we have 18 carbons in the ring, so 18-aniline. It's a bit quicker than 1, 3, 5, 7, 9, 11, 13, 15, 17, cycloheptatrienyl. But we have these two resonance forms that we can draw for this. So looking at that same kind of naming, we could call this 6-aniline. We have our 10-aniline, 12-aniline, so you can see the kind of numbering that they're using here. But anyway, so we have a ring, it's planar, but it has just 4 pi electrons, so we know that this is antiaromatic. Here we have 4n plus 2, because we have 6 pi electrons, so this is aromatic. Non-planar, non-aromatic. Here we have nearly planar, so that's fine. But if we look at how many pi electrons we have there, we have 12 pi electrons, would just be a 4n case, right? 4 times 3, so anti-aromatic. We have 14-aniline, so that would be 4n plus 2, because we have 14 pi electrons here, aromatic. Here, 16, 4n, anti-aromatic. 18 pi electrons, we said that that was aromatic. Now look at our last two cases here. This is a conjugated diene, but we can't go all the way around, right? We have this CH2 that's not in conjugation, so this is non-aromatic. We don't have this delocalization all the way around the ring. Same with this one, non-delocalized, non-aromatic. So non-planar and non-delocalized, non-aromatic. Here is our summary slide of everything that I just said. Non-planar, non-conjugated, non-aromatic, and you can see the different cases for 4n plus 2 or 4n. Questions there? All right, so why is Hückel's rule, why does it exist at all? Well, if we're looking at cyclobutadiene, we have our 4 atomic orbitals that will make 4 molecular orbitals. That's what we're looking at, our 4 molecular orbitals. We have a bonding molecular orbital down here. We have an anti-bonding up here. We have these 2 electrons now that have to be in orbitals. The orbitals are degenerate, and so we have to put 1 electron into one orbital, 1 electron into the other orbital. So this is unstable. We don't have these electrons paired up. So we have these 4 molecular orbitals. The highest and lowest are not degenerate, but these 2 are degenerate, equal in energy, and they are unpaired electrons in them. But if we look at benzene, with benzene here, we have our 6 orbitals, our 6 molecular orbitals. we have these orbitals that are now lower in energy than what they would be, right? To begin, this would be our energy for our atomic orbitals, intermediate energy. So we're lowering the energy, putting them into these molecular orbitals. We have our molecular orbitals that are degenerate here, but we can pair up our electrons. We put one electron in and then one electron, and then we can pair up our electrons. And so now we have all these paired electrons. They're all lower in energy, bonding molecular orbitals. That's going to be more stable. So this is a more favorable electronic arrangement here. So with Hückel's rule, this is 15-7. With Hückel's rule, it doesn't have to just be something that's neutral. It can be charged compounds also. So here we have this ring that is non-aromatic to begin with, because there's no conjugation here all the way around the ring. But this is very acidic. One of these hydrogens here is very acidic. And so if we deprotonate that, then we end up with this intermediate that has a negative charge. We can delocalize that negative charge. There are 5 different resonance forms that we can draw here. So it just says etc., because you know how to do that delocalization. But with that, now we have 1, 2 electrons in the bond, 2 more electrons in the bond, and then 2 electrons here in the lone pair. So we have 6 pi electrons. So that's a 4n plus 2. Now this is aromatic. The anion is aromatic. The starting material is non-aromatic. Again, this starting material, so this is non-aromatic and this is non-aromatic, but we end up with an aromatic intermediate when we do this reaction where we get a carbocation. So when we do this reaction, we can treat it with bromine. That's going to allow for us to lose basically a hydride is gone. So a hydrogen with those electrons ends up being gone in the course of this reaction. So we end up with this salt where we have bromine with a negative, carbocation, delocalize that, a bunch of different resonance forms, 6 pi electrons total. Because that positive charge is there, we can delocalize these electrons. So again, we have our 6 pi electrons, we have an empty orbital here, but we have all these p orbitals because when it has a carbocation, remember, that's also sp2. So all of our carbons are sp2 now in the ring. Instead of being sp3, now they're all sp2. We have all these p orbitals, delocalize that electron density. Questions on this? When things are aromatic, they're very stable. So stable, not going to react very easily. Did someone have a question?
I have a question. Would the product be aromatic as well then?
What do you mean the product? This is aromatic, yeah. This cation,
Okay.
is that what you mean?
Yeah.
Okay, yeah. So once we make the carbocation or the carbanion here for these 2 rings, they are aromatic because they have 4n plus 2 pi electrons delocalized. So now it's very stable. They don't really react. After they do this first reaction, they're stable as is, and so they're not going to be very reactive. So moving on to 15-8, benzene is not very reactive. Things that are aromatic, they don't want to lose their aromaticity, so they don't really react. So benzene doesn't really react. It's definitely not going to do any of the reactions that alkenes do. But it will do something. The thing that benzene can do, what benzene can do, it's called the electrophilic aromatic substitution, where we substitute a hydrogen for an electrophile on the benzene ring. This is called an EAS, electrophilic aromatic substitution reaction. So you need to know the general mechanism so that you can apply it to everything I'm going to show you. Know the general mechanism so that you can apply it specifically, changing out what you see here as E+, change it out to what is the electrophile. But our general mechanism is that the benzene ring attacks an electrophile, and we lose our aromaticity. We don't want to do that, but we do it here in this reaction. We lose our aromaticity. Because we're making this cation intermediate that is stabilized by resonance, it's okay for us to do this. So we have all these resonance forms that we can draw here after we've added the electrophile. Now, why are they showing this hydrogen? Because the hydrogen was there in the beginning, it doesn't go away magically. We have to show the hydrogen going away. We are losing a proton, so we could write minus H plus, or here they're showing you the proton. But we lose a proton where those electrons go into the bond. Here, this carbon has a positive charge. But as it goes into the bond, we make this bond and we restore our aromaticity. We restore aromaticity. So this is the mechanism. Make sure you know this general mechanism so you can apply it to more specific cases. So here's what's happening. We have an aromatic starting material, and we are losing our aromaticity. So this first step is very slow. We have to add in a lot of energy to do this first step because we're losing our aromaticity, that stabilizing force where we have all these double bonds in a ring. But we end up with this intermediate that is stabilized by resonance. So our intermediate cation stabilized by resonance. So once we make that, it's very fast for us to lose a proton and regenerate our aromaticity with this product that we formed. Overall, we are lowering the energy. Overall, this is an exothermic reaction. And so if it's overall an exothermic reaction, the reaction can occur. Even though our first step requires us to add an energy, we can lose a proton fast after that first step, allowing for us to make something more stable than what we started with. So let's look at specific reactions. So our first electrophilic aromatic substitution reaction is the halogenation reaction. So any of our halogens, we'll look at which ones we can actually do, but normally benzene wouldn't react in the presence of a halogen. So we said if we just had over the arrow bromine and carbon tetrachloride, nothing would happen. But if we add in a catalyst, a Lewis acid catalyst, now we can do this halogenation by electrophilic aromatic substitution. So ferric halides, so ferric bromide is what's used here, or aluminum halides, these are going to be catalysts for this reaction. What is our electrophile? Well, remember what bromine looks like? Remember that it's a bromine-bromine bond where we can polarize it, right? We've seen this a number of times before. This is our electrophile. So apply that to the mechanism that you saw a couple slides ago, where we attack the electrophile and we break the bond between the two bromine atoms. In the end, we lose a hydrogen that was on the benzene ring, giving us bromobenzene. This allows for us to make organometallic reagents. We can make a Grignard or an alkyl lithium. So we've already talked about this with our radical halogenations. We said that exothermicity is an issue here. So fluorine is very, very reactive, so the reaction is explosive. So we usually avoid fluorine. We don't use fluorine. And then iodine we also don't use because it's going to be endothermic. Think back to chapter 3. If you did the calculation, I'm not going to do it, but you can do the calculation here. Endothermic, not possible. So we do chlorinations and brominations for the halogenations. All right, so that's our halogenation. Let's look at one more reaction today. We have a nitration. So nitration, we start off with nitric acid. So we have a nitrogen, double bond, single bond, oxygen with a negative charge, and then there's an OH on it. Nitrogen has a positive charge because it's making 4 bonds. Oxygen has a negative charge. I'm not telling you anything you shouldn't already know. We add in H2SO4, which is source of a proton. We pick up a proton, which allows for us to make this intermediate, where we now have a good leaving group. So nitric acid gets protonated. We lose water. And then we end up with NO2 plus. Where's the positive charge? On the nitrogen. The nitrogen is the electrophile because it has a full positive charge. And so with this is called our nitronium ion. NO2 plus, nitronium ion. This allows for us to make our benzene ring, where it's a nitrogen bonded to the benzene ring, and we have a double bond and a single bond. Think about the arrows that you'd have to draw if this is your electrophile in order to end up with a nitrogen still with a positive charge, but one of our oxygens has a single bond with a negative charge. You're going to do a nitration in lab. So I'm telling you this so that you can think, use your brain before we do that nitration in lab, before you write up your lab's mechanism. So here we have our nitrogen as a positively charged nitrogen. This is our electrophile. We'll talk more about reactions that benzene can do later. So that's all for today. I'll see you for lab, I'll see you for office hours, and I'll see you on Friday. Bye, you guys. Have a good day.
Thank you.
I have a question.
Bye.
So for
Go
lab,
ahead.
we just need the mechanism, not the balanced equation.
If you're doing a reaction, you always need a balanced equation
Okay.
and a mechanism, both.
Okay. Thank you.
Uh-huh.
I had a quick question.
Uh-huh.
For a pre-lab, do you want in the reagent table, do you want mineral oil to be included?
No, you don't have to use mineral. You don't have to include that. That's fine.
Okay, thank you.
Uh-huh. Other questions?
I have a question. This is going back to the beginning of the lecture, but when you're going over the one or the conjugated, the 3 conjugated diene,
Uh-huh.
how are you able to tell the difference between the 3 conjugated diene from a benzene ring?
The difference, so you're talking about when we're talking about the energy. The difference here is look at the bonds. They're showing you as the bonds are kind of pulled so that it kind of is like these electrons over here and these, but if the bonds are all equal in length and all in the same plane, then it's actually not going to be separate dienes. It's going to be all these electrons together.
Okay, thank you.
Uh-huh.
I have a question about the 1,3-cyclobutadiene, because you said that it can be a dienophile and a diene,
Yeah.
but it has 4 pi electrons, so can it be like in the Diels-Alder, can you have a dienophile that has 4 electrons? It's just that only 2 are like being okay.
Only to react, yeah.
Okay. And that's always or just this case?
Always, yeah.
Okay. All right, and then
So
same would go for the
it has to be where it is electron poor, and so you see that it is electron poor because we have sp2 hybridized carbons that can technically be pulling away electron density from